Please look here at all of the resistance we get when we start to generate electric current from a wire coil under a bunch of spinning magnets. Now, it's like putting a brake on the magnetic rotor, and it slows down, doesn't want to spin anymore. So if we could reduce the amount of resistance of the wire coil, it would be of great value. Now, Nikola Tesla had an idea to do that almost 100 years ago. We're just going to test today to see whether his idea works or not. Today, we are going to test a hypothesis made by Nikola Tesla over 100 years ago that he could use bifilar wire coils, two-stranded, to improve the generation of electricity. For that purpose, we have assembled 5 wire coils from our laboratory here. These 2 are monofilar, one-stranded, 800 turns, or monofilar with iron inside 800 turns. These 3 are bifilar, 2 strands wrapped together at once. This has 2 times 87 turns. This has 2 times 400 turns, and this big one has 2 times 500 turns. Now the hypothesis was, if we spin those coils under these magnets, I've got 12 strong neo-magnets, bar magnets, arranged north-south, north-south all the way around a rotor so that 1 RPM equals 6 Hertz, and measure the currents made using a multimeter, we can see whether the generation of electricity gets better or worse for monofilar versus bifilar. I've got a little drive motor here to spin the rotor around, and I'm using a 12-volt DC power supply to make it spin. So let's go ahead and do the experiment and see if it works. What I've done now is to place the largest of those wire coils, the large bifilar one, under those 12 spinning magnets, which are powered by this DC power supply and this little drive motor. And I've attached the leads to a multimeter, and we can see that without any current flowing, we're getting about 17 or 18 volts AC generated within the coil. Now we can use different speeds. This particular speed, if you put a red light on there, you can see it's coming out about 277 RPM for the digital tachometer. We can vary the speed from about 0 to 700 and measure voltage and current at every speed. Let's measure current next. Now we're measuring current from the same wire coil. We had to put more power into the DC power supply because of resistance caused between the magnet and the coil when current starts flowing. And for AC, we see at this particular voltage and RPM, we get 0.378 amps AC from that wire coil alone. Now by doing this measurement over a whole range of RPMs for 5 different coils, we can assay how much resistance is in the coil, DC or AC, depending on the RPM and the inductance of the coil, and we can find out whether Tesla's hypothesis was correct. Now here are the tabulated results just for this particular wire coil, which is bifilar, 34 ohms, 160 microhenries, and 1.3 microfarad capacitance. We're taking the RPM from 100 to 700. We're making measurements all the way along. The voltage starts at 4.9, the current at 0.14, and we go all the way up to like 34 volts and 0.44 amps. Now notice the amps saturate near the high level. They don't get any bigger. They start quite low. They don't get any bigger. That's because of AC reactance. So if we calculate then how much resistance is in the coil, we get 35 ohms at low RPM, which is the same as its value at rest, and no AC reactance. And then as we keep going up in RPM to 700, we get 77 ohms overall, 43 of which is AC. So you can see here how the AC reactance increases with RPM from 0 to 700. Quite a big number, isn't it? So that's why we can't make much current beyond the 700 RPM limit. Now we made careful measurements from all 5 of these wire coils, and here are the results. Each coil has a certain inductance L, which can be measured on a meter, ranging from 1 millihenry up to about 160 millihenries. This big coil here has 160 millihenries, for example, the Bifilar. And there are various types. There's a bifilar, monofilar with iron, monofilar without iron, air coil, and another bifilar. And the only thing we find is the AC reactance, or what you call resistance, when we go up to 700 RPM, increases in proportion to the inductance L, in excellent accord with theory. There's a little variation. You can see the 160 millihenry, this big coil, has an AC reactance of about 43 at that value. And this little coil over here, 2 times 87 turns, only has 0.65. So that's in perfect agreement with modern theory that the AC reactance varies in proportion both to RPM, or frequency, and inductance L. Nikola Tesla's hypothesis was that we might be able to place a capacitor in series with any of these wire coils to create what is known as an LC resonance, L inductance with capacitance C, and at a certain resonant frequency it might make electricity more easily. Now we've carefully measured and calculated and tested all of that. It doesn't seem to work. And the bifilar coils also have some capacitance. For example, that one has 1.3 microfarad. That one has 160 nanofarad. And the intrinsic capacitance of those bifilar coils doesn't work either. So it's a good idea, and it'd be wonderful if it did work, but it did not, and we can't make electricity more easily in that fashion. To conclude, I would like to show you again how much resistance we get from a wire coil which is placed under a ring of magnets when it starts to generate electricity. You can see there's a huge braking effect on the magnetic rotor due to Lenz interactions between the coil and the magnets. Tesla had a good idea to get rid of that, or some of it, 100 years ago. I've tested his idea today. It doesn't work. But we'll keep trying, and then hopefully we'll start to make more electricity and the rotor will spin. Thank you very much. With hard work, to the stars.